Hi guys, today I want to talk to you about electrons in the atom. Before we begin, don't forget to get your notes out, highlighters, and colored pencils or pens to write all over your notes today. Okay, let's get started with light. Light exhibits properties of both waves and particles. This is called the dual nature of light. So the wave nature of light is basically you have a electromagnetic spectrum right here, and we call this EM spectrum. Okay, and in this EM spectrum, these are the lights that are different light that is available at different frequencies or different wavelengths. So you have radio waves, microwaves, infrared waves, infrared radiation, visible light, UV rays, X-rays, and gamma rays. So, and for gamma rays, you want to write this down. This is gamma. In case you can't read this, this is actually the gamma symbol. So it's the gamma ray. So notice that under visible light, you have the red, orange, yellow, green, blue, and then of course there's I for indigo and violet light. And when these lights, visible lights, all the colors of the spectrum, when they combine, they usually form a white light. And that's a mixture of all the other visible colors in the visible light spectrum. Okay, so let's talk about a wave. You have something called an amplitude. The amplitude actually, describes the height of the wave. And that tells you how tall or short a wave is. Okay? Then you have something called wavelength. And that's exactly what the word is, the length. It tells you how wide a wave is, or how big or small it is. And then finally you have something called a frequency. So a frequency is defined by how often a cycle occurs in 1 second. In 1 second. And when I say a cycle, I am talking about how many waves. Okay, so when you look at this, a wave could be going from crest to crest, trough for trough, or from the middle to the middle at one end to the middle of the other. And that would be considered one complete wave. So usually we're looking at how many, from trough to trough, how many of these complete waves are actually present in 1 second. So if we go back to the electromagnetic spectrum, let's talk about this. Notice that when you have radio waves usually have a longer wavelength. Because they have a longer wavelength, they would have a lower frequency. Real quick, just to let you know that the symbol for frequency is usually a curvy V symbol, and for wavelength the symbol is lambda. Okay, that is lambda. Okay, so going back to radio waves then, radio waves and the EM spectrum. If you go to radio waves, notice how it says here that it's a longer wavelength. Well, that means that the wavelengths are a lot longer. If they're longer wavelengths, then most probably you're going to have less waves in 1 second that occur. So we usually say that that is a low frequency. Okay. On the other hand, you've got gamma rays have the highest frequency of all the waves in the EM spectrum. And if we say that you get higher waves as you move towards the gamma rays, then we would say higher frequency means that the waves are going really fast in 1 second. So the wavelength itself would be shorter. So we say that it has a shorter wavelength. Okay, So wavelength and frequency are inversely related. As the wavelength increases, you get less waves in that 1 second. But if your waves become shorter, then you're going to get more of those waves that are occurring in 1 second. Let's see. Right here, moving on, it says all colors of light have the same speed. This includes a vacuum and in the air. So we would actually say that the speed of light, and we would just call it V, is equal to 3.0 times 10 to the 8 meters per second. That's incredibly fast. So this is the speed of light that we have. And also, different colors can be described by their wavelength or frequency. So each of these colors, as well as the different waves that we have in the spectrum, they can be described by their wavelength and frequency that is unique to those particular waves. And then, of course, the brightness is determined by the amplitude of the wave. How tall or how short the wave is describes the brightness of the wave. Okay, so moving on. The particle nature of light. So in the early 1900s, Einstein did an experiment called the Photoelectric Effect, and he actually won the Nobel Prize in Science for this. And it revealed that light could not completely be described as a wave phenomenon. So this is really interesting, because what happened is that he used a metal plate, and he charged this metal plate up with negative charges, and then he flashed a visible light to it. Then he checked the charge of the plate. Well, nothing happened to the charge of the plate. The plate was still charged with negative. The plate still had a negative charge. Then he took an ultraviolet light. So we're going to say this is UV light, and he shined it upon this negatively charged metal plate. And what he noticed is that all of a sudden, this metal plate lost its charge. That's because the negative charge, or the electrons, were being emitted from the plate. So every time he flashed a UV light onto the negatively charged plate, electrons would be emitted or would be released from this plate. So basically, he said that the higher the frequency and the lower the intensity, UV light or photons caused electrons to be emitted. From the metal plate. Okay, and that's really interesting. And this photon that he said that it's either UV light, but really what this UV light has is something called massless particles, or photons. So, and this is where the light particle comes in. So this is where you get, this is where Einstein actually came up with a theory that light has a dual property. There's a dual nature of light, where light can be both a wave as well as particles. So really, what does that mean? What that means is that photons, yes, photons are massless, and we have it right here, but photons are packets of wave energy. So let me show you in this drawing. You have a packet right here, that has waves in it, and another packet that has waves in it, and another packet. So truly, what happens is that waves travel in little packets of energy. So you can tell that energy, light is both a wave because it's inside the packet, but then it's enclosed inside a packet right here. So we say that in this case, we would say that there are 4 particles, right? 4 particles or 4 packets of energy that are made up of waves. And that's the photoelectric effect that Einstein received the Nobel Prize for. So we're going to highlight photoelectric effect. Okay, and right here, this UV light, I want you to write the word, maybe in a different color, write the word photons, because that's really what he realized that he was doing, that he was shooting photons in the form of UV light. Okay, so moving on. Okay, so now on to the next page. Let's talk about the particle nature of light. Okay, we now know that photons can carry different amounts of energy depending upon the frequency of the light. Okay, the energy of a photon depends only on the frequency of the light, and the brightness is determined by the number of photons that are present. So what this means is that if we go back to this electromagnetic spectrum right here, what this means, first of all, light or the photons can carry different amounts of energy depending upon the frequency of the light. And the energy of the photon depends solely on the frequency of the light. The higher the frequency, the higher the energy of the light. So right over here, right under low frequency, low energy, and under high frequency, right, high energy. Okay, and it depends, all of this depends on the energy of the light. So over here, when Einstein was performing his experiment, he first tried visible light, shining visible light on this metal plate. But notice visible light is right in the middle of the electromagnetic spectrum, or sort of say, and what this means is that when he tried the UV light, which is at a higher frequency, he was now able to activate the electrons in the plate and activate them where they were eventually emitted. And that's only because UV light has a higher frequency than visible light, which means that UV light has a higher energy than visible light. Okay, so frequency and energy are directly related to one another. Okay, so if we go back to our page, our previous page, so let's go back to the Bohr model. So in the Bohr model of the atom was developed in the 1910s to incorporate both Rutherford's discovery of the nucleus and also the discoveries of emission spectrum. So according to the Bohr model, electrons move in predictable orbits around the nucleus. So let's first draw our Bohr model. We can draw one right here. We're going to draw 4 circles around this nucleus. Okay, so we're going to have, this is energy level 1, 2, 3, 4. And we're going to say that this one right here happens to be at a low energy level. Okay, so it's at a low energy level. And we're going to say that this 4 right here happens to be at a high energy level, which is true. So the closer you are to the nucleus, the lower the energy level. The further you are from the nucleus, the higher the energy level. So what happens is that if you have an electron, okay, let's say it's an energy level 2, and the electron is going from a low energy level to a high energy level right here. If the electron is doing that, and I'll write E for electron, then because it's going from a low energy level to a high energy level, energy is going to come in. So the energy will be absorbed. So this electron will actually absorb energy to go from a low energy level to a high energy level. Okay, so we're going to write here, since electron is going from low energy level, low energy level to higher energy level, electrons will absorb energy. Okay, so on the other side, let's draw another nucleus and then 4 orbitals. Now, of course, I'm just using the solar system model to explain how energy and electrons are behaving. We now know that electrons actually live in those probability clouds. So 1, 2, 3, 4th energy level. And in this case, what we have is now, if we have an electron that is at a low energy level, and that electron happens to move to a, if we have an electron that is at a high energy level, and it happens to move to a lower energy level, well, what that electron is going to do is that it is going to now release its energy. So energy is emitted, or it's released. So what's actually happening is that since electron is jumping from high energy level to a low energy level, the electron will release energy. And that makes sense, because if you're going from a very high energy level to a low energy level, what are you going to do with that energy? Well, you're going to end up releasing it. So going back over here, you have here on number 3, electrons can absorb specific amounts of energy and use that energy to jump into higher energy levels. And go ahead and underline this, where electrons will emit photons of light energy when they return to the lowest possible energy level. Okay, so really what we are saying is that the energy of those photons depends on which energy levels the electron was moving between. So really, electrons will be jumping from one energy level, and they will release or absorb a certain amount of energy. Bohr was studying hydrogen. Bohr was studying the hydrogen atom, but we now know that this is true for other elements also. And so when elements absorb energy, such as on a flame test, the element gives off or emits a characteristic color. And when exposed to an intense energy source, an electron can jump to a higher energy level. This means that it jumps to a specific energy level, and so it absorbs a very specific amount of energy. Okay, and when an electron falls down to the original energy level, it gives off a specific amount of energy at a specific frequency of light. So each element gives off a unique combination of color. This is very true, and we find this to be true. It's the basis of fireworks that happen. So this is why we have fireworks that are of different color, because you're using different elements to emit the energy. Okay, so what happens is that you take your element and you put it in the flame. Once you put it in the flame, those electrons are now, that were once in a low energy level, will now jump to a higher energy level. That is because they're feeling the energy from the fire. But as those electrons eventually go from a high energy level back to their particular energy level, in the process they will release energy. And the energy that they release is in the form of light, which is a combination of different colors. So different elements will jump a different number of energy levels, and they will go back a different number of energy levels. Depending on their jump, the energy that they release will have a different color to it. Because remember, within the visible spectrum, you have different colors of light. You have different colors. So really, what we are looking at here is that these colors will emit at a different frequency. So this is really the emission that we're talking about of light. And truly, this combination that we have is called the color of a flame test. And that's an experiment that can be done very easily to test the color of the element. Okay, so here we have the atomic spectrum, and as you can see, you can see the wavelength of the colors of the different elements. So this is the hydrogen emission spectrum, and you can see the wavelength of the colors that will be emitted from this hydrogen atom. So I'm going to write here atomic spectrum. You can see the wavelength of the colors of the element. Okay? You can see the different colors of the elements. And this concludes our lecture for today on light. Thank you.